So first of all, thanks everybody for joining the very first virtual meetup. And yeah, so David is a C++ developer, very much focused on performance. And he's, well, this is what I verbatim will read from his bio, because I like the sentences. He's measuring nanoseconds at work and at home. So at Optiver, he's writing automated trading systems for options and teaches also modern C++ to his colleagues. And yeah, of course, very honored that you want to do this talk today. And yeah, the floor is all yours.
Thank you very much, Ray. Yeah, thanks also Patricia, Nicola, for organizing this. It's great that we can do this virtual meetup with so many people attending. Maybe even a bit more people than when we do the meetup in Amsterdam. So we're going to talk about C++ tonight. We're going to talk about branches. So let's just say first of all, on why would we want to talk about branches? Why is this interesting, exciting topic? Yeah, it's been a while. I wanted to talk about branches. I guess the first idea is always the same one, is that yeah, we use C++ for performance mostly, mainly, and to write fast code, we basically need to have a pretty accurate idea of what the hardware is doing. We need basically to know what hardware is doing to write fast code. And I think there are a lot of talks about data, about cache, like Strup, Chandler Caruth, Mike Acton, every year, CPPCon meeting CPP. There are many talks about cache-friendly data structure, about basically cache access, how to write performant code, not just looking at the complexity of the algorithm, but memory. And to be honest, on the other side, on the instruction, there are not so many of them. And that's basically what mostly branches are about. So, and then the last idea was that you as a programmer can definitely act on that. So you have basically tools and techniques to help basically instructions and branches. Otherwise, it would be a bit disappointing to just talk about it without being able to do anything about it. Write fast code, as always, energy, performance. In my case, yeah, working, as I said, I'm working at Optiver. In my case, it's mostly latency. Because yeah, I work at Optiver, so we're a trading company based in Amsterdam. About 400 people. We have also 2 main offices in Sydney and Chicago. And there I'm leading a team that develops automated trading system. I'm also still developer, and I teach C++, which is great, by the way, to teach C++ Optiver. It's a great opportunity to really explain the way we do C++ at Optiver. So today's agenda, what we're going to look at, first, yeah, why would we care about branches? What does it matter? What can we get from basically optimizing branch? We're going to very briefly look at the how does a modern branch predictor works, and then connect that with C++ with some ideas, some guidelines. Yeah, look at code performance. Okay, so why does it matter? In short, I think most of the papers agree that we have roughly between 25% of executed instructions are branches. Our modern CPU are superscalar pipelines. So let's do a quick quiz. It's not going to be a quiz because unfortunately I will have to answer the question myself. So we're on a modern CPU, modern Intel CPU 5 wedge. So that means that every single cycle we fetch 5 instructions. We have a pipeline of a 20 stage pipeline basically. Still the same 20% of instructions are branches. So how long does it take to fetch 500 instructions? First question is basically with a perfect branch predictor that doesn't exist, 100% accuracy. 100 cycles. The idea is 5 wide wedge. We just decode and also execute. We do we have a pipeline that is full. On every single time we fetch 5 instructions at the same time, so it takes 100 cycles. Now, if you have a 99% accurate branch predictor, how many cycles does it take? And immediately we jump to 120 cycles. Because so we have 500 instructions, we have 100 branches, 99% accurate. So we have one misprediction. This single misprediction on the 500 instruction caused basically our pipeline, entire pipeline, to be stalled, and we just waste 20 cycles. Now, I think you get it. I can basically just keep on going. 95 accuracy, we have 200 cycles. So so you can very quickly slow down basically your benchmark or just your code in production with that. Now, on last one, on why does it matter? Obviously, it depends on your workload. So you see that depending on what you do, let's take one GCC. So here, basically, this graph compare perfect branch predictor versus perfect cache. Yeah, so you see that depending on the workload, you might have basically more or less influence of the cache or the branch predictor. Or I think GCC is quite interesting. You basically, you only achieve a very, very interesting performance if basically you have both perfect cache and branch predictor. Some workload, like for example, CPack, is basically more subject to branch predictor. So now, kind of a branch predictor 101 in 3 minutes. Key takeaways on any modern branch predictor. I think the main idea to remember is that it's a hybrid approach. It's just not a single algorithm, but it's a combination of multiple predictors. I decided to name 4 just because they're quite simple, but there are more. Let's start with the most basic one. Extremely simple, which is not dynamic, it's static prediction. It's mostly used on modern CPU as a fallback when your dynamic prediction doesn't work, basically when you cannot predict a branch. And usually it's as simple as forward branch is not taken, backward branch is taken. Surprisingly, this works, or unsurprisingly, this works reasonably well, mostly because for loops, this predictor just is going to get a very good predictability. So because we mostly have loops in our program, this very simple predictor, yeah, is not so bad. Local branch predictor. Here we have a table that is called a pattern history table. And we have basically it's a 4-bit table. 4-bit table. So we have saturating counters of 4 bits, and this slightly more complicated predictor just with 4 bits will be able to predict with a 100% accuracy these 4 loops. So how is it going to work? Well, we start on our first iteration. So in my history, I have 4 0, which means which means not taken, not taken, not taken, not taken. And we just, the first time we encounter that loop, we are going to set taken on that history, because we basically arrive at the end of the loop and we take that loop to do the first iteration. Same for the second iteration, third iteration, and then at the end we don't take the loop anymore. We exit. With this 4 bits table, now that we train the predictor on that specific branch, the next time that we encounter that branch again, we are going to predict perfectly every single conditional jump, taken, not taken. Basically, we just learned that with the 4 bits table. So the way the CPU obviously use that table for local branches is that there is one PHT. There is basically a set of PHTs, and basically the key is usually the program counter. So we basically index. So we have a kind of a hash table with a key is our instruction pointer, and the value will be one pattern history table. Complexify it slightly more. If we have basically, let's say, an if in this loop, we can see, this basically if will basically make the loop break in some exceptional case. And in order to avoid this exceptional case to immediately, let's say, break our pattern in the most case, the trick here is to use hysteresis with just 2 bits counter. So instead of having 1 bit, so instead of immediately, as soon as we break, change our decision to, let's say, taken or not taken, we use a 2-bit counters, which we increment or decrement. So in order we add some hysteresis in order to not immediately with very small sensible change to change the prediction. Global prediction, global branch predictor, sorry, is correlation with past branches. It's the same ID, it uses the same data structure. And the CPU basically learns that, well, if the first branch is not taken here, this one is definitely never. And it makes sense, but you can actually obviously complexify that code with, say, vector condition, complicated condition. You clear the vector, make it the same, like, right? So from the CPU point of view, so you can effectively learn some quite, seemingly a complicated correlation between branch pretty well. And last not least, there is a simple predictor for like branch. We're going to talk about bias branch during the rest of the talk because bias branch are quite interesting. And the CPU know how to recognize bias branch, which is basically a branch that is going to be, let's say, 99% of the time taken or not taken. And for this, is going to use an extremely simplistic predictor, such as a last prediction, for example. So that all the structures that we looked at, mostly this pattern history table, indexed basically on the instruction pointer, are just not being polluted by a very biased branch. Okay, so now let's just look at now that we know a little bit more like how it works in the hardware, let's look at what we can do on the C++ side. I'm going to start with the first one. I'm going to almost skip this one. It's extremely basic. I just wanted to have it in the slides because it's pretty obvious, but I still have to mention it. But obviously, you can remove unnecessary branch. This helps overall your branch predictor, right? So if you move away from runtime to compilation time using templates, and if context, you're going to use less instructions. You're going to remove a branch or actually several branches. You're going to have a lower pressure on all the structures that we looked at before. So this is just going to work. So how does this look like? That's just one example, let's say, of how we would do it. So we use a technique at Optiver. You have a runtime. You have, let's say, a configuration that comes from a XML file, for example. You read your value. You want to have that configurable, so you want that flexibility. But then you convert that runtime branch by using templates or if context. So that's a classic one. Still have to name it, but it obviously works because you just remove the branch entirely from your code. And usually that enables more optimization, which is why it's quite interesting. Small variation of that technique is basically to get rid of virtual function calls. So when you use virtual function calls, you basically have indirections and interaction on branches hidden there, and you can basically use the same technique to get rid of them without compromising any performance. So yeah, here the example is even I'd say less exciting. It's basically just a classic template that you use, maybe with some explicit instance. But just by removing that, you help directly the structure used by the branch predictor. Right, so let's move on to something a bit more, slightly more complicated, also well-known techniques, but maybe not all its consequences. You can basically help a lot your instruction cache. So here actually we don't really help the branch predictor. But by giving a branch bias or by giving indication on the branch itself, we help our instruction cache and also page faults. The idea is that so we have the concept of basic block. A basic block is basic structure where we have basically one entry point and one exit point in our code. And by giving indication to the compiler, GCC or Clang, we'll be able to basically have the optimal layout to optimally put all your basic block together in order to have them basically to have the layout of your code as the code is going to be executed most of the time. And this is going to help a lot let's say not just the prefetcher, but in general basically your instruction cache. So let's look at code. And that's basically how you do it. But that I think is pretty standard, I guess. It's new. There is the new syntax with C++20, but before we didn't really wait for it. We were already using it. That's the example. So we have now two different cases. We have an unlikely case where we throw an exception, and a likely condition, like a condition that is likely to be taken, where we make it throw the same. And that's basically by the likely or unlikely, we don't really influence the branch predictor in any way. It's not going to change anything for the branch predictor, but the layout of the code though is going to change completely. What you see on the left is that the entire, so this entire code here that I highlight is the code that we will usually not take. Basically the code we don't care, like the cold code where we throw an exception. And you see that in this case, GCC clearly move it out. We have it here, and we just jump. While on the other case on the right, the entire code that I highlighted is basically now there. So this is, I think this is a great example because this, now with an exception, but with any code, you could imagine, I think the best example would be logging. We have a lot of logging also at Optiver in our code. And it's definitely important, but it's interesting to see how you can basically just pollute and hurt your instruction cache on the prefetcher just by having one line of code, basically. So effectively, I did look at what's the size of this code on the right. It's roughly, in this case, throwing an exception, 70 bytes, so slightly bigger than a cache line. So you can imagine that if you have a code with quite a few of these branches, let's say, not just throwing, but just doing something like a logging or throwing, you're just going to jump from one cache to another cache line. And most of the time it's really going to hurt performance because the prefetcher is not going to be able to go that fast. So code layout is effectively one of the main interesting part of this keyword, or not really branch figure, but it's related to branch, definitely. If anyone is interested, yeah, for the actually just to look at the performance, like, so how much exactly does this help our code? In general, obviously, you're not going to get. I mean, we should never expect should never expect on search optimization a ×2 or ×3. But in general, it's going to be you're going to get some nanoseconds, microseconds here and there. So you can find this table is from the proposal itself that has been written to the standard committee, and these numbers immediately are a consequence of the instruction cache. Now the good news, because I don't want to entirely advocate you to after this talk start adding the slightly unlikely literally everywhere. I think the good news is that there were some great improvements brought by GCC 9 recently and also Clang about this basically code hot-cold code partitioning, and also the branch, this basically branch weighting. So basically how it works in the compiler is that for every single branch, even without your keyword, for every single branch a condition, there is an kind of a decision tree. There are some weights. There is a weight being put there by GCC or Klein. And what's very interesting is that in the recent GCC or GC9, GCC sees that if you, for example, if you throw an exception, it is going to correctly, let's say, weight your branch. It's going to put it as unlikely. And it's a combination of weights. So it's quite complicated, but it works really well. So effectively, recent GCC or Klein will never, if you have an if and then an exception, will always, that's a good news, we always lay out your code like this. So you don't need the unlikely keyword. Effectively, they do more than that. I just named two here, but it's quite complicated. They can basically, they will detect null pointer checks. Yeah, as I said, exceptions on other things. And eventually, all the weights are going to be combined. And this is basically what's going to lay out your code. Third ID, almost the same as the second one. It is basically again about instruction cache, but we go a bit maybe I think we go one step further. And here, basically, it's a technique that Andrei Alexandrescu described. So it's definitely nothing new that I'm saying here. It's described in a talk about inline destructor at Facebook, where you look at the performance of inline destructor, because destructors are usually, if you just don't declare them in your CC file, just basically, if they are defaulted from the, if they are defaulted, sorry, they will be most of the time inline. And there is a cost. So we basically analyze the cost of inline destructors in the Facebook code base. Here, I just applied this trick to branches. So one step further of the ID, of the second ID, ID3 is basically to move away even further your cold code. You put it in a function and you make sure that it's not inline. And this way you really achieve like the, you know, what I mentioned like in the previous slide, basically your ideal data struct is a vector. Keep basically all your cold data together, cold and hot data together. So that's why we all love stud vector. We don't want stud set. We don't even really want hash maps, although we use them. And for code, it's kind of the same, and that's basically one way to do it. I don't think you need, I don't think you need this no inline really, but it's just basically about moving stuff into functions. Sometimes you're a bit lazy, I think. As a developer, we tend to leave stuff in the header file. And by experience, I definitely measured that it hurts performance to have all this inline code everywhere. Again, for the same reason that you have basically just code bloat on just all that dead code, cold code in the middle of your warm instructions. All right, this is a slightly almost the last one, a more complicated idea. It's unpredictable branch are definitely interesting, right? Because if you cannot predict them, at least if you cannot predict that the CPU is not going to predict them correctly, you're supposed to get rid of them. Huh? You cannot just get rid of all your branches. That would be too nice. So what you can do is you can use a conditional execution. Let's look at a small example. So we have basic for loops, vector unsigned ints. We have a condition, and we just adjust that with a threshold. Very basic for loops. I measure the performance. Okay, I use Google benchmark. This is my function, by the way. It's called benchmark. The one that we looked, this one, the one that we looked before. And I call it with with my vector, and my threshold is going to be max divided by 2. So I hope that when you're convinced that this branch is not going to be predicted because I picked the worst number that I could pick, right? So that's picking on purpose for that example. I picked the median. Oh, by the way, sorry, generate a vector using uniform in distribution. So this is really the worst case. It's not a branch you can predict. So one code that basically your compiler is in general going to compile is going to just use a branch, right? So you will have a branch there, and you will have some some performance for that loop. 700 megabytes per second. Basically counting in bytes per second, like the number of basically ints or bytes that we can that this function can let's say consume, can process. So now let's tell the compiler. Right, I also print. Sorry, I forgot about that. Also print, just for information, IPC instruction per cycle. We are roughly at 1.7. Just to, it's not great, but it's not completely. It's not that bad. Now, if we can tell the compiler that this branch is not predictable, we can remove the branch and use a condition by a C move, so predicated move. And this works really well. Basically, we get something between like roughly 5 times speed up. So how do we do that? Right. Forgot again. IPC. We are now 2.5. Better and better. By the way, you see that here we have. If you pay attention, we basically have, and that's classic when you measure something. It seems that we have more branches per second than before, but that's just because we are faster. Because we are much faster, indeed, we process more branches. But so overall, yes, more branches, but it's basically better for us. Recent client on GCC give some new directive for that. So you can tell the compiler that a branch is not predictable, and you can influence basically the assembly generated there. Very last one. Same story with GCC. You can basically go even further than Klein here, because you can really give this probability. So it's like, it's not unpredictable, but it's like very, very likely. I'm not sure if I will, I'm not sure if I completely, if I would write code like this. I don't think so. I don't think we are entirely ready for that. Very likely. But it's still very interesting to see that you can now very accurately tell the compiler that if the branch is very likely to be taken, please use a branch, because the branch predictor will love it. Otherwise, you use CMove. And that the performance, I mean, here, well, I didn't measure it, but it's basically the same example as before. It's basically CMove versus branch, if you can predict it or not. So it depends also on X, on your distribution, basically. So branches in a nutshell. Few things to remember. Unpredictable branches are special, definitely. Code layouts is, yeah, so you're not going to be able to help or influence the branch predictor itself. Kind of, if you remove your branch, and you can help the structures. But the most, I think, the key takeaway is that instruction cache on code layouts is what you're going to influence. So that's basically what you're going to look at. And you can help your compiler by setting branches bias. And last but not least, I think this is also maybe one of the most important points. This should be your very last step of optimization. If also there are more talks about cache, it's because you can definitely get the difference between different cache layouts is much bigger than what you can get actually with branch. So if you start looking at optimization, or if you instructions, or if you start adding that to your code, yeah, make sure that all the rest is already beautiful on fast. And this was my last slide. Thanks.
Cool.
Do we have any?
No, first, thanks a lot for the talk. But indeed, now we can do some questions. There's nothing cute, so maybe people don't have any questions, but but yeah, now would be the time to ask if you want to. I see. I have one. Okay, Niels, I'll give the. Hi, Niels. You should be able to say something. Oh, you're muted.
Yes. Thank you very much for this very interesting presentation. Can you say a little bit more about this Andrei Alexandrescu findings of the a destructor that could be outlined and the effect of it?
Yeah, definitely. So I'm going to, so first of all, I'm going to find the exact title of the talk, and I can post the URL in the chat because it's been a while. I think it's been at least 5 years. Well, the idea in short was, so as I explained, it's mostly not about branch predictor, but mostly about the instruction cache. Basically, just to increase the number of hits you have on your L1 instruction cache, and then basically Andrei Alexandrescu was saying that right with a basic C++ struct with just let's say one stud vector, maybe another container. The problem is that the thing what's being a bit hard is that you have a defaulted destructor that takes care of everything, obviously, and it's effectively quite big. It's a lot of code, and this code is invisible. On what Andrei was saying is that the problem of this invisible code is that most of the time it's inline, and then it just it basically just you have it literally everywhere in your function. You don't see it, but it's there in the assembly, and it hurts your iCache.
Ah, yes. Okay, makes sense. Yes.
Cool. So we also got some questions in the chat, so I'll just read them both. Or yeah, does it make sense for me to read them, or? Okay, I'll just read them. So
Maybe don't have the chat,
so okay, the first question is from Muklek. I am a student learning C++ in my free time. Where can I find more information about what you talked about today? Any books, for example, or?
Books. That's actually a good question. To be honest, I would recommend you to follow. I don't have a name now in mind, but I would recommend you to follow. It's a bit more. This talk is more about basically CPU microarchitecture applied to C++. I don't think there is a book that really put that in practice in C++, but in general, learning C++ and then maybe following some course online from some university. I'm sure there are plenty of them. CPU microarchitecture course. I think that is, I think, my recommendation. Otherwise, there is a book, but maybe not for beginners. It's basically the Intel manual, the software, basically the optimization book from Intel. It's a bit hardcore. You have to be maybe a bit prepared for this one. Sorry, otherwise I have a name. I will post it on the chat, but there is Agner Fogg. Agner Fogg also has a lot of resource. Yeah, exactly. Yeah, that name.
Yeah, I think it was sent to the wrong chat, so I'll forward it.
It was the link I wanted to post. That's great. Thanks,
okay.
Thanks, Costa.
So I think the URL should be. Okay, so another question from another David. Do you see much difference between the code generated by GCC and Clang, and do you prefer one versus the other?
I'm going to be really honest here. I mostly use GCC. I don't think. We always see some small differences, but there is no, at least from my experience, at Optiver, we also looked at that. Is Clang faster? Let's look at it. We didn't see any huge difference, no. But code is different. The code is definitely different, but performance-wise, no, they are quite on par.
Okay, nice. So we have time for another question. So another question from Alex: is concurrency used in Optiver trading in the Optiver trading engine, or is it too long to synchronize?
Yeah. In short, by concurrency, okay, I guess we would have to define what's concurrency on trading engine. If we are talking about, let's say, engine, the very end engine that we use to send orders, the one that really needs to be fast, no, there is no. It's not really, let's say, locks or no. Yeah, we have basically one, let's say, log-free structure we use. So we could call that concurrency. But in general, I'm not sure exactly. The question is maybe a bit vague, but we don't use any, let's say, multi-threading. We use some multi-process approach though. So we have some log-free structure there, yeah.
Cool. So so strictly speaking, our schedule should be that the talk is now done. Maybe one more question or a short one is going to be okay. I forgot to check if anybody raised his hand, so I think maybe everything is answered now. Well, for now, I mean.
Right. I will find the link of the talk I was referring to. Andre exchanged free talks. I will post it.
Cool. And
Thank
maybe
you.
you have a chance if you still have a question in the chat afterwards. Okay, but well, thanks a lot, David, for your talk. It was indeed
Thank
very
you.
interesting.
Yeah,
And
thanks. Bye.
cool. So yes, without further ado, I think let's hear it for Sergey.
Thanks, Optiver,
Cool.
for providing us nice multi-participants Zoom account, so we can have a lot of participants. That's nice. So thanks, David, for a nice and very good presentation about prediction and optimization. And as we already seen in David's presentation, C++20 is on our door. But if we start thinking about how to build our modern C++ programs, we sometimes see that a lot of people or a lot of operating systems still have a CMake 2.8. And for your interest, 2.8 was released in 2010. So it's almost more than 10 years old software we are trying to utilize for latest standards of C++. So it looks a bit weird. So now I'm going to tell you a bit about CMake 310-316 because it depends. Some features are really fresh and some are already stable since 2017, but anyway, it's better than 2010. And few friends of CMake, like CTest and CPack, that are less known tools, but also could be very handy to deliver software. So one slide about me. So I'm a software engineer in Viasat. Viasat is a satellite communication operator. Headquarters in California, USA, and in Amsterdam we have a small office for 10 people now. So we are starting development here also. I have 10 years of ISO standard C++ development for cross-platform software. So generally, I wrote software for Mac OS X, Linux, Windows, a bit of ARM-related for Android, and so on, and embedded in general. And consequently, I had to know a lot about software system design at early stage of product and ending with a deployment and delivery end user artifacts in a reasonable way to let our customer use it in most handy and useful form. So my presentation will contain multiple parts. Biggest part is a glossary because we need to identify our terms and words to understand each other. Then I give you a short overview of example project I'm going to define or describe, and then particular separate features of CMake or other tools per slides, as with real examples from real project. So in our glossary, we need to understand what is a CMake itself, CTest, CPack, what files we can use for configuring, for providing to users, and so on. What is a CMake module? What is a CMake config? It might not be well known. What is a target? Why it is important to use targets in CMake? What is a CMake properties, variables, arguments, and parameters? A lot of different words, and most of them are well known. But when we start working with CMake, they have some ambiguity with meaning of all these terms, so we need to agree on them. So CMake is our main tool that generates our build script to build our software. And CMake has multiple steps to actually provide us binary artifacts from our source code. First step is the generation step, when CMake processes its own script and prepare our build environment to compile our source code. Then we actually run build step, when we actually run compiler under the hood. Then CMake is able to run installation step to finalize our binaries accordingly target platform. I will cover it later a bit. Also, CMake provides some tool for testing, for packing artifacts into target platform packages. CMake has a very rich command line and UI tool some people prefer to use UI of CMake because you can see a lot of flags, ticks, and so on at the same moment without digging into documentation and --help argument of command line. CMake provides a lot of modules out of the box, and it worth to investigate what is there, because maybe your problem already have been solved by CMake maintainers. CMake implies that you will provide configs for your projects, for your libraries, to actually help people use CMake. And CMake has a breathtaking and mind-blowing flexibility, and it leads to a lot of confusion, issues, and really ugly code in CMake when a lot of people reinvent the wheel. So just to avoid it, we need to think how to use CMake properly. As a part of CMake bundle, there is another separate tool called CTest. With CTest, you can register your tests. Most likely, it relates to unit testing, but also you can use any test runner you have. So if you have some component test as a separate runner, you can also use CTest without relation to a main project. CTest run tests in parallel, sequentially, extensive logging of execution, and so on. CTest provides reports in multiple forms like XML or in XUnit, I believe. And also CTest has integration with another tool from CMake bundle called CDash. CDash is out of scope for today because it's more for serious CI/CD, because CDash requires a standalone server with dedicated installation. Another useful tool from bundle is a CPack. CPack provides you unified way to distribute your software. It is a highly configurable, and CPack generally just works. So when you have your binary artifact, most likely you would like to deliver it not as a bunch of binaries in folder or in zip archive, but in a Debian package for Debian related system, NSys installer or MCI installer for Windows and so on, or maybe a framework and bundles for macOS X. So CPack provides support for all main system and a few fancy system also. CMake use some terms for directories and files. So later I will refer to some of them, and we need to understand what it is. So source directory is our main project directory where all our sources are located, where main CMake list file placed, and so on. Also, when we run CMake, we usually use separate directory called build or binary directory. I can refer to build or binary, depends on context, but it's actually the same directory where all your temporary files created by CMake, and also where all your artifacts will be created after installation and packing step. And install directory is a very important thing, is a place where your software will be installed on target platform. So generally, this installation directory is not your host or build host directory. It is your desired place for your installation. Install prefix and prefix path. So install prefix you specify during using CMake when you would like to say where your binaries will be installed. And later I will show it how exactly to use this install prefix. But prefix path, regardless of similarity in naming, it's a completely other thing, and you use prefix path to point CMake during generation and build step, where is modules and configuration files are placed. Prefix paths are widely used for cross-compilation when your build environment differs from your general host environment. And also you can use prefix paths for some fancy tricks with extending build environment without affecting build system, build host system. CMake use some conventional file names like a CMake list.txt is a main CMake list CMake file where you actually specify and describe all your build process. Also, it expects some files with suffixes config.cmake and -config.cmake, and case is important now. These files are your project config file. So I refer to them as a config files. find something.cmake is generally modular files, and CMake comes with a lot of modules exactly with written in find something.cmake files. And sometimes when you see a lot of projects supporting CMake, you will see just some files ending on CMake with some random names or meaningful names or whatever. It's just a piece of CMake scripts that could be used independently or as a part of CMake list.txt or as a part of modules and so on. And later in presentation, we will see some non-conventional naming that ends on .in. They came from my example project, and generally it is templates that used by CMake to instantiate with inserting actual names during template parameters. And I will show it if we will have enough time for it. So modules, as I said, modules are usually stored in find something.cmake files. Modules provided by CMake vendor. Usually module is treated like a CMake standard library and contain a function, algorithms, and macros that extend CMake behavior. So all CMake functionality written in its modules and available for inspection in its binary folder. As CMake vendors always said, contribution is welcome. So if you think you wrote a nice and useful module, you can always contribute it. And if it falls under some contribution guidelines and so on, it will be accepted. And in next release, a lot of people will start using your module. And more important things, module is not specific to your project. So you are able to write modules, but most likely you are going to extend CMake itself, not your project. Comparing with a config, naming for config files refers to your project, to your library. And usually these config files written by us, by authors of a project, library, frameworks, or whatever that we are going to deliver. And they are delivered as a part of project. So usually when we install some devel packages on CentOS system or full package in Arch related system, you get headers for your library, some debug symbols maybe, symlink for libraries, and also most likely and highly desired to get config files for this library to easy integrate library into upstream project or downstream to your user project. It's better. So config files are referring to project components, usage, and dependencies. So it means that they actually extend your project, and they are very critical to guidelines and best practices how to use and how to write configs, because between version 2 of CMake and version 3, there was no good guideline on in their documentation, and a lot of projects who officially support CMake cannot utilize CMake in full form. And to avoid it, it's better to spend effort for investigation how to write a good config for users. Properties. Properties is a named field on different objects, on targets, on functions, on variables, or whatever. Properties are might be CMake managed and project managed. And properties depend on CMake arguments and parameters. Sometimes properties looks like variables, and we don't need to mix them because they have a similar naming rules. But variables is usual as a normal language variables. They could exist or not exist. They may has value or may not has value, and so on. Properties could be property value could be assigned to variables, and variables could be used to set property. Arguments is a well-known command line arguments with a name or flag form, and parameters. It's not very usual practice. When we call CMake or CTest, we can pass some parameters to it. With -d name and value, we pass parameters that will become a variable or property in our CMake list. Also, CMake use environment variables as its parameters, or Some of them could be found in CMake cache txt entries. CMake cache txt is a full map of all variables created by CMake at generation step and contain all representation of everything that CMake collected during generation. Generally, CMake authors to edit some entries in this CMake cache file txt, but personally, I didn't find it really useful, except the case when your project is really big and you would like to save time on generation, on full regeneration. Okay, so short overview of project we are going to describe. Project is, it has a C API library, so it provides a library with C API and headers. It is a cross-platform, so it supports Mac OS X, multiple Linuxes, and Windows, different builds. It depends on project-specific binary blobs, like resources. It depends on external libraries. As usual, it might be a source code dependencies, header-only library, or static linking library, or runtime dependencies provided by system, or delivered together with a project itself, but shared linked. So looks like a usual project that we usually sell to our customer. There we can see some screenshot of source code layout. On root folder, we see folders with good naming, I believe. CMake that has some CMake list, CMake files as extension. Depends folder contains source only external dependency. Examples folder contains our example application with short sandbox sample how to use our library on the end user side. Headers contains our include files, and sources contains all our sources. Res folder contains our binary blobs that we would like to deliver together with our project, and they goes to customer as is. And now, CTest. When we wrote our project, when we wrote our unit test, we would like to run them. And CTest provides us easy way to combine all available runners under single hood and run it at once in our Jenkins as a part of CI/CD, or locally to be able to run all our tests and so on. So first we need to enable test, call function enable testing. It's available for our CMake list txt out of the box. Then we do our configuration of build, and then we register our runner, which called on slide ut and tp with a add test function. Add test function has two arguments: name of test and test runner. After it, with a CTest call in our build directory, we will get run of all our registered tests by default without any output, but we can enable -- verbose to see test runner output. And as we are talking about modern CMake, starting from version 3.10, CMake provides a useful module for Google Test users. They have integration between Google Test Runner and CTest utility. So if we add line include Google Test into our CMake list txt, and then instead of adding test manually, we call gtest discover test function using our runner name, this module enumerate all tests in our runner and register them one by one under CTest. So instead of having blind call of single executable, we will see a more usable output from CTest. And you don't need to enumerate all these unit tests manually. Module that does it for you, and it is really helpful when you have 100 unit test and you don't want to update CMake list manually every time you add or remove unit test. And now, if someone has question about CTest or introduction, that's a good moment to ask. Okay. Okay, we can move on, I believe. Yeah.
Okay.
Next tool is CPack. So under subtitle, you see how generally you
Oh
can
wait,
run.
there is a question.
Yes, perfect.
I think, right or not? Does it speed up? Is it the question? Probably first versus second method.
Sorry?
I mean, if it's faster or not, I think.
Uh,
I hope
it is a very, I don't know how to say it, because this source code is actually a CMake source code. So it does not affect our build time and doesn't affect our runtime. But if you have a lot of unit test runners and a lot of tests inside, then yes, GTest discover test call can slow down a bit your generation step. So it can you can get some disadvantages from it for full regeneration, but as CMake is a very powerful tool and supports incremental generation also, most likely you don't need to regenerate whole project every time after every change. You can use existing build directory after first generation.
cool. I see there's also another question from Marius. What is the difference between add test and creating a separate binary with tests?
That's a very good question. CMake with CTest tool is not aware about your structure in project. So a test function actually creates test in terms of CMake or CTest based on top of your runner. So you can create one single runner or you can create multiple runners. But how to register them in CTest or CMake, it depends. So for my example, I use multiple unit test runners per module in my source code. So obviously for real project, I have 20, 50, 100 of unit test runners as a separate targets, as a separate executable. I don't want to run them manually in Jenkins one by one. And that's why I prefer to use registration them as a test in CTest. And then with a single call CTest in build directory, I run all of them registered. So it's a bit different approaches. You have a test as a unit test, you have a runner that execute your test, and you have a test in CMake that actually execute your runner. And that's why GTest discover test from CMake 3.10 really helpful. You actually skip this extra proxy entity in a chain.
Okay. There's one remark in the chat also, and then probably we should move on. It's like Michael continued with, I noticed that using CTest is much slower than using directly an executable from GTest. I don't know if you have similar experience, but...
Correct. Yes, correct. Because CTest actually intercept all output of your runner. And if you have a very extensive output, and if you actually provide this output to std out from CTest, it might slow down. Yes. But as I said, it depends on size, amount of project, and so on. And also, you always can disable this verbosity in CTest. And by default, it's not really verbose. It only reports you success or not.
Cool. Right.
Okay, next tool, CPack. So CPack actually gets all your binaries after compilation and pack into target platform package. CPack supports a lot of formats. I enumerate only a few of them that I actually use. So for me, it's zip archives, RPM for CentOS and Debian. And as you see here, you have to include CPack component for component-based and enumerate manually all components. Syntax looks really weird, and it's better to refer to documentation what exactly CPack add component means and how to use it better, because it's really weird from my perspective. But then we just configure our packing process. We have a lot of configuration general for packing process. We have a lot of configuration per format. So CPack archive component install, we enable separate components for archives. Also, we enable separate components for RPM and so on. And at the end of this configuration, we include CPack module from CMake, and that's it. After this, after successful build, we run CPack -g and our desired format, and CMake will create us our packages. Important remark, obviously CMake relies on operating system tool. So by default, out of the box, you cannot build RPMs in your Debian system because there is no RPM build tools. You can install them separately if your distributive provides, and you then able to build RPMs on your Debian. There are a few caveats and problems for this cross-compilation in that way. So I keep it as an exercise for you if you are really interested, because I recommend it in straightforward way to use your target platform as a build environment when all tools are available for CMake. Then it's much easier to debug and much less issues later on runtime and on installation. And also, as you can see here, as an example, you can explicitly enumerate all dependent packages exactly in the form as your target platform expects. So for RPM, we enumerate RPM names, and for Debian, we enumerate Debian packages as they are available in repos. CPack also supports after discovery for that RPM build tool provides from CentOS. And again, chance to ask question about CPack.
I think no, for now.
Yeah, and we always can come back if necessary.
Yeah.
Next important part of modern CMake is targets. So targets are usually treated in CMake as our library name we would like to build, or our executable name we would like to build. So short introduction, we create target with functions like add library, add executable, or add custom target. We append some source files that CMake should compile to actually generate our library, and so on. Also on this slide, you can see how you set some different properties for our target. And the important things, we register, we configure, I think, library dependency also on target level. So if you start searching in the internet about CMake, roughly, a lot of tutorials of CMake based on old CMake version 2.8 or 2.8.12, something like this. And they have a recommendation to add your include directories and libraries for linking with an include directories call. And I even forgot the name of function, how to add libraries for any targets, for any libraries in your project. So it actually make a big mess in config, in the compilation command lines, because you mix all your parts at the same time. So it is highly suggested and recommended to use a target-oriented approach and treat targets as a minimal thing you can operate and interact in CMake. So on slide, we create library called neon with some source code. We also create an alias target for our library with namespace extension. I will show later why it's necessary. Then we set up which library we need to link with our library, and we don't specify -L flag. Instead, we use also targets of CMake. These targets might be object files. These targets might be interface libraries who treat it like a placeholder for our header files and so on. So targets are very powerful tool. Then we set some compile features and compile definition specific for our libraries, set some properties, include directories, and so on. And our target could be checked in CMake list file with a if condition. So if we would not have a target, we pass into this condition.
So there's a question from Niels about this slide. Maybe we can do it.
Yes, exactly.
So the question is, if you make the CXX STD17, a private target, or a private target compile feature, can you still use C++17 in the interface, in the header?
That's a very good question, because it actually refers to a way how I organized this project. So if we look at next slide, and I believe this slide answers this question, I create another target called headers. And headers, in subtitle of slide, if you see. So I create an interface target headers, also with alias target. And this headers target does not say about C++ standard, because as I said, my library provides a C API. So obviously I cannot use anything from C++ and should stick only to external C definition and plain C function declaration. So this division between header library, header target, and the actual implementation target implements a dependency injection approach in dependency injection practice pattern. When we divide our public interface from our implementation. So generally, having headers as a separate interface library, I don't limit myself with a way how do I implement these headers. And I don't believe that customer will do it, but I can implement the same interface with another target, with another library at the same project to try compatibility, to check compatibility, to try different tests, to run some optimization or whatever, and deliver two libraries at the same time with a single header target. And it could be really handy for users because you can provide a version 1, version 2 implementation for the same API. And it doesn't limit you with a standard use in your implementation because your interface is completely independent. And as we are discussing this anyway, here we see another useful features of CMake called expression generator expression. It is embedded condition, I would say, that could be used for some functions call. So here at first line, I say that during build step, my headers should have as include directories my current source dir include folder. But when I do installation, I should forget all my project source directory, instead use only include directories that is GNU compatible, like a USR include or Optiver include or so on. I think this part, how we configure export configuration header for our library, I skip it for now. If we'll have time, I can describe it better. And then when we define our interface library for our headers, we are able to install it in efficient way in CMake recommended way, I would say. So first, we have to tell to CMake that we have targets, our headers target. We are going to export it into Neon headers export file and include destination for our target is our CMake install include directory. CMake install include directory came from GNU install dir CMake module and implements GNU standard of all naming, all folder naming, and so on. When we define, when we describe to CMake how to install our target interface headers, then we install our export file. So the second line of installation is we say we would like to install export Neon headers with namespace Neon. And if you remember from previous slide, I added namespace explicitly for all my targets into the destination. And data root dir is usually a share, USR share or PT share folder. And I control where exactly these files go. File will get name neon header target.cmake. And this file is a part of my project config. I think later we will see our config file. So we need now to remember this name, neon headers target CMake. And we define component devel. This is our component for CPack tool, actually. 2 more lines. It's just an example of how we also can install directory folder as it is, also as a part of component, and another folder with some generated files in our binary directory. And now we are moving immediately to a configs, as we are already touched. So as I said, CMake provides install DIRS module with valid and standard naming for GNU system. Also, CMake provides CMake package config help, and this line you can see a good description in documentation. It's just save our time to don't reinvent the wheel next time, every time. And last line, that's important line, where we actually install our project config file into our destination. So all these paths, CMake install data root dir or install dir from previous slide, are relative to our install prefix. So we don't care a full path. We rely on CMake to instantiate absolute path for us. We only use these variables. Config file, that's how our config file looks like. So as you see, we have a .in file, which is a template. Template in CMake contains placeholders for instantiation. For our particular case in config file, we use a package init placeholder, is a standard placeholder provided by CMake to add some utility functions and macros that we use later in our configuration. So check required components call will be inserted by CMake on instantiation. In our config file, we have to manually enumerate all our targets we would like to provide to our user. So at this line, include, I don't know actually, do you see my mouse cursor or not? I hope so. On this line, we include our neon headers target.cmake we've got from previous slide on installation step. And second line, the similar approach, but for implementation. So our configuration will contain headers and library itself. So our user, and on subtitle slide, you can see how our user can use our project now. In his CMake list, our user write find packaged our name and required components, headers and neon. So headers our header library or our headers, and neon is the actual implementation. If you would like to provide version 2, you can say, okay, you can try version 2 neon, for example, underscore version 2 or whatever, without any conflicts, problems, and so on. Also on this slide, you can see how we can use module approaches, moduleless, to extend our project and help user to use our project. So as I already mentioned, config relates to our project. Modulus relates to CMake. But sometimes we would like to use in our project external dependencies that doesn't have CMake configs. For my example, I use TensorFlow as dependency, but TensorFlow itself does not provide CMake config. So to avoid any manual handcrafting compiler flags configuration or link libraries configuration for my user, I wrote manually find TensorFlow module that I deliver as a part of my project. But I install it into separate subfolder of my project, so I don't mess my customer operating system. And in my config file, I manually add this my local path to a CMake module path variable. CMake module path variable contains semicolon separated list of all paths where CMake looks for modules. And then when I do find dependency. Find dependency is a part of CMake find dependency macro module from CMake already. Find dependency is a replacement of find package specially designed for config files. CMake will look for TensorFlow also in my module folder. So it gives me ability to don't overload my user with a search in TensorFlow, with providing TensorFlow as a library to for compilation and for linking and so on. So my user just use my library as it is, and all configuration, all dependencies are hidden from user in my config file, in my implementation, and so on. It was a bit complex, so I expect some questions might be asked.
Okay, just a quick time update. We are now been like a little over 40 minutes. We've had questions in between already, but if there's questions about this, we can indeed do them now. Or
yeah, okay. And as I already said, that's how user use. So no any TensorFlow mention, no any dependency specification, nothing. All configuration does it for you. And if some dependencies will not be satisfied, CMake will print error and say, hey, new library requires TensorFlow, no TensorFlow found, solve it somehow, like install TensorFlow, for example. Okay, next, modules. It's a brief description that and mostly like a summary. So CMake provides a lot of modules, and it was to investigate what modules are available and how they can help for your particular needs. As example, GNU installers for naming, CMake package config helpers for creating config files, CPack and CPack components for packaging, Google Test for integration with testing. A lot of modules that helps you to find libraries in build environment. So find package boost, find package curl, find package CUDA, find package whatever you can imagine, most likely already available and used. Be aware some modules has issues because they're really rarely used. Okay, how many time we have?
Well, officially just a few minutes, but yeah, I don't know if we can, of course, go on longer.
Okay, then I skip. I will not try to duplicate myself and jump to command line of CMake. So as I said, CMake is highly configurable and flexible. And sometimes variables, parameters, and arguments can be confused. So most likely, we write our CMake list for our project in most generic way with a purpose. We would like to compile our project and pack it into some packages. We should not care about compilation flags, optimization, whatever else, coverage, and so on. Most of this functionality could be configured during instantiation CMake on the fly. So as an example, first line, we tell CMake, please enable position independent code. So we don't need to pass pick flag to GCC manually in our CMake list. We just need to say CMake, please enable position independent code on, and CMake adds this flag to compiler if compiler supports it, and so on. CMake install prefix, as I said, that's a desired place where our library will be installed. CMake build type, this is a let's call it meta configuration of compiler flags. So CMake has 4 default build types: release, debug, release with debug info, and release with performance optimization. And depending on build type, it sets different compilation flag, linker flag, and so on. So you don't need to manually enable -03 if you would like to have optimization. You can just choose a release or release with performance optimization, and CMake does a lot of configuration for you. -S and -B arguments for source directory and for build directory. I think it's worth mentioning them because they were hidden in documentation till last version and only recently were open for public. Then we can use CMake to run actual build without calling underline tool. So by default on Linux system, for example, CMake use GNU make files as a generation result. And obviously, after generation, we need to run make with a make install, or whatever. CMake provides a good proxy call named CMake -- build with your build directory, and it will call your underlying tool. So it works for Microsoft Visual Studio, it works for Ninja build tool, it works for Make, and much more. Also highly configurable, and you can pass some arguments for underlying tool also. Next line, I think here we can mention that we can the same way configure CPack, so we can pass some CPack parameters also through CMake command line, and this a bit confusing. So because we actually call CMake with generation step, but we also pass CPack configuration parameters. When we call CPack later, we are not able to provide the parameters, similar parameters, and that quite tricky with a CPack CMake integration between. And as I said, CMake supports Visual Studio, and since recently they are able to choose host platform and target platform independently, because Visual Studio recently introduced this x86 and x64 compiler. So now you have ability to configure them independently without any auto detection or coupling them together. Also, you don't need generally specify, do you want to have a static library or shared library? Let future you to choose. So with a -d build shared libs, you can say to CMake to build shared library or static library. Sometimes you should stick to one particular type, and you can pass this argument to add library function. But generally, and it is recommended way to don't hard code this expectation, and much more configuration for CMake. In summary, I think so. It is recommended way to use open object-oriented approach even with CMake. Regardless, it looks like a script. Anyway, it is a fully featured programming language. So our targets is our objects to interact. Modules are reusable pieces of code and extend CMake. Configs are our interfaces for users and extends our project. We are able to reuse code as much as possible, even with CMake, with its include function. It is recommended to keep global scope clean. So we use a target-specific function instead of global ones. We persist global properties, global variables, and global state in our CMake files and don't alterate them. It makes sense to keep the entity ownership. So configs owned by us and modules owned by CMake. Some CMake files are useful snippets that could be used in configs or in modules, depends on. And we are able to configure our build with parameters and arguments. So let the future you make the choice. Today we need a static library, tomorrow we need a dynamic library. Without hard-coded property, we can just rebuild our project as is without any changes in source code level. We can use CMake parameterized value instead our variables, and it's highly recommended to use relative path everywhere in project, because to have relocatable build, to have relocatable packages, and to have a relocatable files to be installed everywhere, regardless of your target platform. I think that's it, and open for questions now, because we're out of time.
Yeah, first, thanks a lot. And indeed, if we have some questions, we can still answer them. In the meantime, I've been looking at my own CMake file. I can definitely add some improvements because I am still putting like the FPIC, all of that kind of flags manually.
Modernize your
Yeah.
CMake file.
And I think the function you were trying to find was add definitions. Could it be that one or not? Like
Yes,
just
yes.
add a flag
add
to everywhere.
definitions,
Yeah.
everywhere, yeah. And I think
I'm also using that. Not proud
while
of it.
we are waiting for questions,
Yeah.
sometimes we are limited with upgrading our compiler because it depends on operating system and runtime. But CMake, we can grab CMake from their official website, put it locally somewhere in our built environment, and use latest version of CMake regardless any target platform. Just keep in mind that your config file will be used by your user, and you need to limit features in your config file with your user CMake version. But what features used in your CMake list, it's up to you. So latest version is 3.17, and move on.
Yeah. All right. So there's a bunch of questions rolling in. I've just in case people are really need to go or something. Then first, thanks for attending, and thanks again to our speakers and Optiver also for organizing. So we can just continue now, I think, with the Q&A, and then because we still have some time, and I guess some people can stay a little longer. Okay, so I'll read the questions. So first one from Elena. Hey, do you you use CMake in mono repo type? Do you use CMake in a mono repo type project? Are there any pitfalls? And do you think you always need a top-level CMake file in this case?
That's a very good question, and I jump to this picture. So CMake list.txt is our main CMake file, but we are not limited to how many CMake lists to have and how to combine all of them. So if we talk about monorepo, it depends of a life cycle of this monorepo project. So if you have a single project that is not modularized right now, and you would like to use CMake, you just use a one CMake list that describes everything in your project, and you don't have any problems. Later, when you start decoupling components, decoupling modules, and so on, you can introduce separate CMake lists that describes this particular module, these particular components. And it is a recommended way by CMake, again, to have this separate CMake list self-contained. So I think I don't have slide with it, but if we look at my CMake list, you will see that top-level CMake list has own project statement that actually describes to CMake that this is our main project entry. But headers also has project, and examples folder also has project entries. So when I combine all CMake lists all together with add subdirectory call from CMake, CMake use add subdirectory to introduce new project in project-oriented build system like a Visual Studio, but project function in CMake tells to CMake how to set some variables. And generally, I can take, and actually what I do, I take my subfolder, example subfolder as it is now in my project, copy it somewhere, and in other place, I'm able to call CMake again with examples related CMake list only. And the same CMake list is used as a subdirectory of a main CMake list. So it's up to you how to combine. The only remark I think worth to mention, sometimes in old guidelines, you see that every subfolder in your project layout contains CMake with only one directive at subdirectory and one level below. There is no strict rule to don't use it, but personally, I don't see any value to have a CMake list on top level, CMake list on subfolder, CMake list on sub-subfolder, and so on, where a lot of them has only add subdirectory call. So it's better to decompose your project in more reasonable way, and how exactly do it, it's up to you, because CMake list, it has a relative path, so no problems with monorepo, no problems with combined repo. Also, if you have a dynamically created repository on the fly, you also can use CMake, but it's a bit advanced feature as an external project, for example, or conditional inclusion. Yeah. Next question.
Sorry, I guess my internet was a little unstable for a while. I glitched out. Okay, yes. I see my ping indeed went up for a bit. Okay, yes, there's more questions. So Kirill asks, could you tell a little bit about toolchain files?
Yes, toolchain files are a small asterisk.cmake file that contains a lot of variables used by CMake to configure cross-compilation. So all these variables are available in their documentation, and you can pass all these variables in command line. As an example, you can specify your compiler name, compiler path, or system name, system version, and so on. Toolchain file is just a snippet to enumerate all these variables, to don't have a very, very long command line, and have a more or less reproducibility and good naming what exactly these variables means. That's actually a toolchain file. So it's a replacement of variables.
Cool. All right. So another question. When you say we can apply object-oriented programming principles to CMake scripts, do you mean concepts like inheritance and composition? And can you give an example?
That's a very good question, because I referring to a software architecture principle, but not a language features. So CMake itself, it's not an object-oriented language. But as we all know, some languages provides things for object-oriented, some not. But object-oriented design, it's not a language dependent. If we look at C, GStreamer, for example, GStreamer is a highly object-oriented, written in plain C. So the same approach might be used in CMake. So as an object, you use targets. As its fields and methods, you use a target specific functions of CMake and target properties. That's it. This is your object. You are able to use inheritance and combination and composition, because CMake provides functions and variable scopes and macroses. But as this presentation is for beginners and intermediate, I would not introduce a big mess how to keep CMake clean and don't reinvent wheel and don't repeat a make file with CMake and whatever. So there is no inheritance and composition on language level, shortly.
Cool. I think maybe we can do the last question. So from Christoph, when starting a project, do you have any template?
Yes, I have. And if you write me in Slack, for example, I will give you a link to my GitHub with a template I used for creation new projects. So on slide now you see one real project I used, and also I have the similar approach for 2 more projects and template for a new one with a short description how to actually instantiate template for a real project.
Cool. Okay, so I see one more question from Niels, and so I'll read it. If all targets in your repo are C++17, would you use global set CMake CXS standard 17?
That's a very good question, especially when I point several times to don't pollute the global namespace and global state of variables and so on. So yes, you are able to do it. And sometimes it makes sense. But for example, my project I used as an example has targets Ubuntu and CentOS 7. CentOS 7 is too far from C++ 17. But at the same time, I don't want to limit myself when I implement library. So yes, I can use as global variables, but where is a guarantee that tomorrow you will not need to port your project on old platform or limited platform or whatever. When you have a per target configuration, you have better granularity and configurability. It might introduce some overhead for maintaining, but flexibility versus few lines of changes, it's up to you. So yeah, it's a more personal feeling.
Cool. So, okay, one more question. It's an infinite source of questions. So, from David, what sources do you suggest for learning more advanced features of CMake?
CMake maintainer published a very, very good book called Mastering CMake. And you can easily find link and book itself on their website. So if you look for cmake.org, you will find this very, very good book that describes everything from basic level to, I think, intermediate. Some advanced features, you need to dig inside CMake documentation for particular version, because some variables, some things described only in documentation. And also they have very good articles on their GitLab, kitware.gitlab.org, I believe. Anyway, link is available on the CMake maintainer website, official one, where you also could find a lot of real examples and actual examples, not from ancient time. Yeah.
Cool. I see Christoph also
Yeah.
sends a message, so I'll just paste that as a message in the chat. So another recommendation for a good source. Cool. All right, I think that's it. Thanks for answering all the questions. There's more questions. I don't know how I don't mind keeping this channel open, but we can also move to Slack if you want to. I think people are starting to leave, so maybe we should
jump to Slack.
Yes. So Luis, I will copy paste your channel, your message to Slack.
Okay, then I'm stop sharing, and thank you all. Thank you, Optiver.
Yes. Thanks.
I hope everyone has fun.
Yep.
Okay. Thanks.
Thank you all. Great presentations.
Thank you. That was really
Definitely.
nice.
All right. See you next time, I hope. And if anybody that's still in the chat, we still look for more talks. So
yeah, because we all have beer prepared for Meetup.
Yeah, I can imagine. Cheers. So thanks again, and see you next time.